Hello there. Welcome to the third of these lessons on electrolysis. Hopefully you've worked your way through the introduction and also the molten electrolysis. I'll watch that video from the RSC as well. You do really need to get your head around molten electrolysis before we start on aqueous. Things are a bit more complicated with water involved, and so do make sure you're fully secure on the molten electrolysis before you start on this topic. All right, well, let's get rid of the webcam there and let's get going. Okay, so as I mentioned, the presence of water complicates things slightly because water ionizes. As you can see here, water is a weak electrolyte, not very good at conducting electricity because it doesn't really have ions, but a very small proportion, only about 1 in 10 million molecules of water, splits up. It ionizes to form H plus and OH minus ions. And we can show that in an equation here. So there we go. Let me get my laser pointer out just to kind of highlight two things. So here we go. We've got our water molecule. And here we've got this equilibrium arrow. Now, we haven't done too much on equilibria yet, or reversible reactions. Some of you may have covered this earlier in your schooling. We cover it back in the first year here at Hampton. So maybe if you were here in the first year, you covered there. Perhaps if you join in the third year, you may not have come across that symbol before. But what it means is it's a reversible reaction or an equilibrium. In this case, we're kind of showing that whilst water does split up to form H plus and OH minus ions, they also then can recombine and form back to water. And actually, it's only a very small proportion of the molecules that actually do split up into ions. As I say, only about 1 in 10 million. But some of them do. And that's important because if I've got an ionic solution like sodium chloride, I've now got 4 ions present. I've got the ions from the ionic compound, the sodium ions and the chloride ions, but I've also got present hydrogen ions, H plus, and hydroxide ions, OH minus. Okay, so that's going to complicate things a little bit. And if we think about the ions that are attracted to the negative electrode, so if we cast our mind back to the molten electrolysis, let's say of zinc chloride, of course it was the zinc ions, the positive zinc ions, that were attracted to the negative electrode. And again, there'll be the positive metal ion will be attracted as well this time, but also will the H plus ions. We've got 2 positive ions present in this aqueous solution. So the positive metal ion, whatever is forming the salt, and the H plus. Similarly, with the positive electrode, there are going to be 2 ions attracted to that. The non-metal negative ion from the salt and OH minus ions from the water. Okay, so that means that our simple ideas of what happens to the electrodes has to be refined somewhat because at each of the electrodes there are 2 different ions, and the question is which is going to discharge. So we've got some rules to learn for that, and that's what we'll go into next. So the rules for predicting the products at the electrodes. At the negative electrode, what we've got to think about are the positive ions that are arriving. So we've got the positive metal ion and also the H plus ions. Now, the key to deciding which is discharged is all about reactivity. And in essence, the less reactive element forms. So we're comparing hydrogen with the other element. So if the metal is above hydrogen in the reactivity series, hydrogen will form. And if the metal is below hydrogen in the reactivity series, then the metal will form. Let's just think about that a little bit. So let's think about some examples. Let's say we're electrolyzing sodium chloride solution. So the sodium ions and the H plus ions will be attracted to the electrode. And we have our little test. We say, right, sodium. So, well, sodium's pretty high in the reactivity series, isn't it? And so sodium is above hydrogen, and so hydrogen will form. Okay, so we'd expect to see hydrogen. And that makes sense because let's imagine some sodium was made. Well, we all know what happens when you drop sodium into water. You get hydrogen, it fizzes.
So that kind of makes, I think, intuitive sense. So something like sodium chloride, the sodium ion would form sodium metal if it was to form. That's high in the reactivity series, much higher than hydrogen, so it doesn't form. It is hydrogen that forms. So let's now think about something else that's lower at the reactivity series, so something like copper. So we've got, let's say, electrolyzing copper sulfate solution, let's say. The copper ions and the H plus ions are attracted. We do our test here. If the metal is above hydrogen, well, copper isn't. And so it is not hydrogen that forms, it is the metal that forms. So if we electrolyze copper sulfate, then it is copper metal that forms. Okay, so a little bit of reminder of our reactivity series. If it's high in the reactivity series, we form hydrogen. If it's low in the reactivity series, we form the metal. Actually, the positive electrode is a little bit easier. What we need for this one is to test whether there's any halide ions present. If there are halide ions present, then it's the halogen that forms. Okay, so if it's a chloride, bromide, or iodide, then we make chlorine, bromine, or iodine. So that's nice and straightforward. Otherwise, it's oxygen. Okay, and the oxygen is coming from the water. So bit easier, I think, that rule to learn. If it's Cl minus, Br minus, I minus, then we get Cl2, Br2, or I2. Anything else, sulfate ions, nitrate ions, etc., we're going to get oxygen gas, O2. All right, so make sure you get those rules learned, and then we'll put them into practice. Okay, so let's look at applying those rules then for our first compound, the electrolysis of a solution of potassium bromide. So let's think about the negative electrode first. So of course, the negative electrode, the positive metal ion is going to be attracted. So that's the potassium ions, so K plus ions will head towards the negative electrode. But of course, remember, we've also got H plus ions heading there as well. Oh, crumbs, let's get trying there. H plus ions. Okay, good. So we've got K plus and H plus. And then conversely, at the positive electrode, of course, we've got the bromide ions. So they're going to head there, but also the hydroxide ions. Hydroxide ions from the dissociation of water. Good. So now we need to use our new tests to decide what is formed. Okay. So at the negative electrode, potassium versus hydrogen. Well, of course, potassium, we all remember, that's super reactive. Bursts into flames. We see a lilac flame when we drop it into water. So it's not going to be potassium, it is hydrogen. So that's hydrogen there. Good. Excellent. Let's carry on the negative electrode, seeing as we're partway there. So we've also got the crumbs. The pen on this is not great. Anyway, so let's go there. So we've got hydrogen ions, H plus, arriving at the negative electrode, and we're forming hydrogen gas. So again, we've got our diatomic product here. So we've got to make sure we've got two of those arriving to make the H2. And of course, each of those hydrogen ions, we've got two H pluses, we're going to need to gain 2 electrons. There we go. So there's our half equation. Oh, crumbs. Let's get rid of that line there. There we go, 2 electrons. Good. So 2H plus 2 electrons going to form hydrogen gas. Perfect. So that's what we'd see. So we see some bubbles. That's what we'd see at the negative electrode. We see some bubbles of hydrogen gas. Oxidation reduction. Always at the negative electrode we get reduction, because it's the negative electrode is chock full of electrons, and the hydrogen ions there are gaining electrons to form hydrogen gas. Brilliant. Okay, so let's turn our attention to the positive electrode, bromide versus hydroxide. Those are the 2 ions that are arriving. The test here is quite straightforward. Is there chloride, bromide, or iodide present? The answer is yes, bromide is present, so we form bromine. So the half equation here is going to be absolutely familiar to you from our molten electrolysis, very similar. we're going to need 2 bromides because we've got 2 atoms of bromine in the molecule, and each of those bromides is going to give up 2 electrons. There we go, half equation there. Of course, that is oxidation. Perfect. Okay, so that's what we're about with this aqueous electrolysis. Kind of thinking about an extra step at each electrode. So here with the electrolysis of potassium bromide, we'd see hydrogen gas, so bubbles of hydrogen gas at the negative electrode. We'd see bromine forming at the positive electrode. In solution, that would kind of look like an orangey brown solution forming around the positive electrode. And also left behind, let's just have a quick think about what's left behind. Because, of course, the potassium ions and the hydroxide ions, the potassium ions and the hydroxide ions are not being used up. So actually, we're kind of leaving a solution of potassium hydroxide behind. But anyway, I think that kind of covers all the key points. And effectively, what we need to do is just do some more practice at this to think about different scenarios and different ions. Okay, so that's potassium bromide. What you need to be doing is comfortable basically dealing with any ionic solution. Okay, so we'll try a couple more and see how we get on. Okay, so let's look at our next substance, our next solution. That's copper 2 sulfate. So the blue solution that we know well from making our copper sulfate crystals. So let's think about the negative electrode. Of course, positive ions head towards the negative electrode, and the two positive ions present are the H plus from the water, and the metal ion, the copper 2 ion. And then flip side, looking at the positive electrode, also got the sulfate ion, SO4 minus, and the hydroxide ion coming from the water there. So let's just make that a little bit niche there. OH minus, good. So let's now focus on the negative electrode. Well, hydrogen ions, copper ions, both heading towards the electrode. What forms? Is it hydrogen gas or copper metal? Well, copper, low down in the reactivity series, and it's the lowest of the two that forms. So this time we're going to make copper metal, Cu. The half equation here looks very similar to what we might write for a molten electrolysis. Got copper ions arriving, copper metal being formed, then we've got this 2 electrons forming. So just as with the molten electrolysis, the 2 plus charge is gaining 2 electrons. So that number there are the same. Good. So that's that. Oxidation reduction, of course, negative electrode, it is reduction, gaining electrons. Turning to the other electrode, sulfate ions versus hydroxide. The rule we've got here, is there a chloride, bromide, or iodide present? The answer is no. So this time we're forming oxygen gas, O2. Now, this is the trickiest half equation, I think, in electrolysis. And so I might suggest this is one to learn. All the others you can figure out, I think, as you're going along. But really, this is one to learn. So I'm just going to write it down. So the oxygen comes from the hydroxide ions, not from the sulfate. So that's something to bear in mind. We're forming oxygen. Oh, crumbs. This pen. Let's have another go here. That's my arrow. Oxygen gas. And trying to get in the way here. So 2H2O and 4E minus. Okay, so 4 hydroxide ions arrive to produce an oxygen molecule, 2 water molecules, and 4 electrons. You can see we've got 4 oxygens and 4 hydrogens on both sides, and the charge is balanced as well. There's 4 negatives on the left and 4 negatives on the right. But that's a bit trickier to come up with in an exam, so I think that's one I would commit to memory. The others, like the copper one on the other side, we'll just work that out as we go along. Of course, opposite electrode, opposite process, that is oxidation. So copper metal, so at the negative electrode, we see the pinky brown metal of copper deposited on the electrode. And at the opposite electrode, the positive electrode, we'd see bubbles of oxygen gas being produced. Excellent. We'll look at one more, and I think probably then you'll have got the hang of it, and then it's really over to you to practice some questions. All right, so final one then. Nitric acid then. So nitric acid, the final one we'll look at. So without any further ado, let's think about the negative electrode. So here we're not electrolyzing a salt solution, we're electrolyzing an acid, but there are lots of ions present, so it conducts electricity just as well. And let's think about the negative electrode. Well, here actually is a little bit easier. We've got the H plus from the water, but more importantly, we've got the H plus from the acid. So indeed, there is only one. The pen's playing up there. We've only got one ion. We've got the H plus ion. So quite simply, it must be hydrogen being formed. And so the half equation is exactly as it was before. 2H plus. H plus 2 minus goes to 4H2. Oxidation reduction, the hydrogen ions are gaining electrons, it is reduction. At the positive electrode, we've got two ions arriving, got the nitrate ion from the acid, also got the hydroxide ion from water. The rule we've got, does it have a halide? Answer, no, there is no chloride, bromide or iodide present here, so we're forming oxygen gas. Okay, let's get rid of that. Oxygen gas. Half equation, that's the one we're going to learn. The others we can work out in the exam. This one we are going to learn. We're going to commit to memory. It's 4OH minus, going to form O2, 2 water molecules, 4E minus. Can I just squeeze that in there? Just about. Maybe let's have another go at that. 4E minus. There we go. Good. Okay, so that's the one we're going to learn. Oxidation. Terrific. Okay, so that's the end of this lesson, practicing aqueous electrolysis. This is one of the required practicals for the AQA GCSE, one of the 8 practicals you need to know, so definitely worth looking at applying these in that practical work, these principles, and hopefully you get to see the different products forming at each of the different electrodes which stack up to these rules. Okay, so definitely want to look closely at, but other than that, it's really over to you now to practice lots and lots of these half equations and thinking about what products are formed. Excellent. That's the third of 4 lessons. The final lesson is looking at industrial electrolysis, so applying all of the things that we've done so far to how we do some industrial processes. Look forward to seeing you next time. Cheers. Bye now.